So today we will discuss chapter number 23, that is Introduction to Transport Layer. So we know that transport layer is located between the application layer and the network layer. It provides process-to-process communication between two application layers, one at the local host and other at the remote host. So the communication is provided using a logical connection, which means that the two application layers, which can be located in different parts of the globe, so there is an imaginary direct connection through which they can send and receive messages. As you can see in this figure, we have a logical connection at the transport layer, and this logical connection is imaginary direct connection through which the messages can be sent and received. So the responsibility of the transport layer is to receive the services from the network layer and to provide services to the application layer, because it is located between network layer and application layer. Now see this figure. This figure shows you network layer versus transport layer. Now we know that the first duty of the transport layer protocol is to provide process-to-process communication. So a process in an application layer entity, or you can say running program, is that it uses the services of the transport layer. So the network layer we have discussed earlier in chapter number 18 to 22, and we know that the network layer is responsible for communication at the computer level, that is host-to-host communication, and network layer protocols can deliver the message only to the destination computer. So this is an incomplete delivery. The message still needs to be handed to the correct process. So this is where a transport layer protocols work. So transport layer protocol is responsible for delivery of the message to the appropriate process. So this figure shows you the domain of a network layer and the domain of transport layer. So as we had said that transport layer protocol provides process-to-process communication. So the most common one is the client-server paradigm. As you can see, we have a client over here, we have a server over here. So a process on the local host is known as client and needs services from a process usually on the remote host, which is known as server. Now this figure shows IP addresses versus port numbers. IP addresses and port numbers, they have different roles in selecting the final destination of data. The destination IP address defines the host among the different hosts in the world. After the host has been selected, the port number defines one of the processes on this particular host. Now it shows ICANN ranges. So this thing we have discussed in chapter number 18. So first go through chapter number 18. You will recall this topic. So here we have divided the port numbers into three ranges. They are well known, as you can see. Then the next one is registered. And the last one is the dynamic port or the private port. So well-known ports ranges from 0 to 1023 and are assigned and controlled by ICANN. These are the well-known ports. Then we have registered ports, which ranges from 1024 to 49151 and are not assigned or controlled by ICANN. They can only be registered with ICANN to prevent duplication. And thirdly, we have dynamic or private ports. These ports ranges from 49152 to 65535 and they are neither controlled nor registered. So they can be used as temporary or private port numbers. Now this figure shows you the socket address. A transport layer protocol in the TCP/IP protocol suite needs both IP address and the port number at each end to make connection. So the combination of an IP address and a port number is called the socket address. So it is combination of both. As you can see over here, we have IP address also, port number also. So combination of IP address and port number is called socket address. The client socket address defines the client process, just as the server socket address defines the server address uniquely. So to use the services of the transport layer in the internet, we need a pair of socket addresses: the client socket address and the server socket address. So these four pieces of information are part of network layer packet header and the transport layer packet header. The first header contains the IP address and the second header contains the port number. Now this figure shows encapsulation and decapsulation. We know that to send a message from one process to another, the transport layer protocol encapsulates and decapsulates the messages. So encapsulation happens at the sender side. When a process has a message to send, it passes the message to the transport layer along with a pair of socket addresses and some other pieces of information which depend on the transport layer protocol. The transport layer receives the data and adds the transport layer header. The packets at the transport layer in the internet are called user datagrams or segments or packets, depending on what transport layer protocol we are using. So generally, we refer to transport layer protocols or payloads as packets. Now decapsulation happens at the receiver side. When the message arrives at the destination transport layer, the header is dropped and the transport layer delivers the message to the process which is running at the application layer. So the sender socket address is passed to the process in case it needs to respond to the message received. Now this figure shows multiplexing and demultiplexing. Whenever an entity accepts items from more than one source, this is known as multiplexing, that is many to one. And whenever an entity delivers the item to more than one source, this is known as demultiplexing, that is one to many. So the transport layer at the source performs multiplexing operation, and the transport layer at the destination performs demultiplexing operation. So this figure shows you the communication between a client and a server and two servers. Three client processes are running at the client side. They are P1, P2, and P3. The processes P1 and P3 need to send the request to the corresponding server process which is running in a server. The client process P2 needs to send a request to the corresponding server process running at another server. Now the transport layer at the client side accepts three messages from three processes and creates three packets. So it acts as a multiplexer. The packets 1 and 3 use the same logical channel to reach the transport layer of the first server. Now when they arrive at the server, the transport layer does the job of demultiplexer and distributes the messages to two different processes. Now the transport layer at the second server receives packet 2 and delivers it to the corresponding process. Now whenever an entity produces items and another entity consumes them, then there should be a balance between production and consumption rate. So if the items are produced faster, then they can be consumed. The consumer can be overwhelmed and may need to discard some items. And if the items are produced more slowly, then they can be consumed. The consumer must wait, and the system becomes less efficient. So the flow control is related to this issue, and we have to prevent losing the data items at the consumer side. So here we have two concepts, that is pushing and pulling. Here the delivery of items from a producer to a consumer can occur in two ways. So the first one is pushing and the second one is pulling. If the sender delivers items whenever they are produced. Without a prior request from the consumer, the delivery is referred to as pushing. And if the producer delivers the item after the consumer has requested them, then the delivery is referred to as pulling. Now, when the producer pushes the items, the consumer may be overwhelmed and there is a need for flow control in the opposite direction. So, we need to prevent the discarding of the items, or in other words, we can say that the consumer needs to warn the producer to stop the delivery and to inform the producer when it is ready again to receive the items. So when the consumer pulls the item, it requests them when it is ready. And in this case, there is no need for flow control. So in communications at the transport layer, we are dealing with 4 entities: sender process, sender transport layer, receiver transport layer, and the receiver process. Now the sending process at the application layer is only a producer. It produces message and pushes them to the transport layer. Now the sending transport layer has a double role. It is both consumer as well as producer. So it consumes the messages which is pushed by the producer. Then it encapsulates the message in packets and pushes them to the receiving transport layer. Now the receiving transport layer also plays 2 roles, as you can see in this figure. It is the consumer for the packets which is received from the sender, and the producer that decapsulates the message and delivers them to the application layer. So the last delivery is normally pulling delivery. Now the transport layer waits until the application layer process asks for messages. Now here we need at least 2 cases of flow control, from the sending transport layer to the sending application layer, and from the receiving transport layer to the sending transport layer. So although the flow control can be implemented in different ways, but one of the solution is to use 2 buffers, one at the sending transport layer and other at the receiving transport layer. So buffer is basically set of memory locations that can hold packets at the sender and receiver. And the flow control communication can occur by sending signals from the consumer to the producer. So when the buffer of the sending transport layer is full, it informs the application layer to stop passing the messages, and when there are some vacancies, it informs the application layer that now it can pass the messages again. So when the buffer of the receiving transport layer is full, it informs the sending transport layer to stop sending packets. And when there are some vacancy, it informs the sending transport layer that now it can send the packets again. Now in the internet, since the network layer is unreliable, so we need to make the transport layer reliable. So if the application requires reliability, so now reliability can be achieved to add error control services to the transport layer. Now this is error control at the transport layer, where we have a transport layer at the sender side and the transport layer at the receiver side. So the error control at the transport layer is responsible for detecting and discarding the corrupted packets, and it keeps track of lost and discarded packets and then resend them again. And it recognizes the duplicate packets and discards them, and buffering out of order packets until the missing packets arrive. So error control is not like flow control, which involves only the sending and the receiving transport layers. Now here we are making an assumption that the message exchange between the application and the transport layer are error-free. So in this figure, you can see the error control between the sending and the receiving transport layers. So as with the case with flow control, the receiving transport layer messages, the receiving transport layer, it generally manages the error control most of the time by informing the sending transport layer about the problems. So we have sequence numbers. So error control requires that the sending transport layer knows which packet is to be resent, and the receiving transport layer should know which packet is a duplicate or which packet has arrived out of order. So this can be done if the packets are numbered. So what we can do, we can add a field to the transport layer packet to hold the sequence number of the packet. Now what happens when a packet is corrupted or when it is lost? The receiving transport layer can inform the sending transport layer to resend that packet using the sequence number. And the receiving transport layer can also detect duplicate packets if two received packets have the same sequence number. Now the out of order packets can be recognized by observing gaps in the sequence numbers. Now from the sequence number, since they use modulo 2 raised to the power m, a circle can represent the sequence numbers from 0 to 2 raised to the power m minus 1. Now the buffer is represented as a set of slices, which is called the sliding window, and it occupies part of the circle at any time. Now at the sender side, when a packet is sent, the corresponding slice is marked. When all the slices are marked, it means that the buffer is full and no further messages can be accepted from the application layer. Now, when an acknowledgement arrives, the corresponding slice is unmarked. Now, if some consecutive slices from the beginning of the window are unmarked, the window slides over the range of the corresponding sequence numbers to allow more free slices at the end of the window. So this figure shows the sliding window at the sender side. The sequence numbers are in modulo 16 because n is equals to 4 and the size of the window is 7. So here you have to note down one thing, that the sliding window is just an abstraction. The actual situation uses computer variables to hold the sequence numbers of the next packet to be sent and the last packet to be sent. Now, most protocols show the sliding window using linear representation. So you can see here we have a sliding window in linear format. Now here the idea is same, but it normally takes less space on paper if we will draw it on paper. This figure shows this representation. Now both representations tell us the same thing. If we take both sides of each diagram and bend them up, we can make the same diagram. So if you will join the last with first, obviously you will get a circle shape. So it's same. There is no difference at all. Now in a connectionless service, the source process, that is the application program, needs to divide its message into data of different sizes which is acceptable by the transport layer and deliver them to the transport layer one by one. The transport layer treats each chunk of data as a single unit without any relationship between them. Now when the first data arrives from the application layer, the transport layer encapsulates it in a packet and then send it. Now to show the independency of packets, you have to assume that a client process has 3 chunks of messages. Okay, message 0, message 1, message 2 to send to the server process. Now these messages are handed over to the connectionless transport protocol in order. Since we have said that there is no dependency between the packets at the transport layer, so the packets may arrive out of order at the destination and will be delivered out of order to the server process. So here you can see the movement of packets using a timeline. And here, as we have made an assumption that the delivery of the process to the transport layer and vice versa are instantaneous. So this figure shows that at the client side, the 3 chunks of messages, that is message 0, message 1 and message 2, are delivered to the client transport layer in order 0, 1 and 2. So because of the extra delay in transportation of the second packet, the delivery of messages at the server is not in order, as you can see. It is that first of all message 0 arrives, then message 2 arrives, then message 1 arrives. So if these messages belong to the same message, the server process may have received a strange message. The situation would be worse if one of the packets were lost, since there is no numbering on the packets. So the receiving transport layer has no idea that one of the messages has been lost. So here the situation will be worse if one of the packet will be lost, since there is no numbering on the packets. So the receiving transport layer has no idea that one of the messages has been lost. So it just delivers 2 chunks of data to the server process. So here you can see message 2 is delivered out of order. So the above 2 problems arise from the fact that the 2 transport layers do not coordinate with each other. The receiving transport layer does not know when the first packet will come, and it also does not know when all the packets have arrived. So we can say that no flow control, error control, or congestion control can be effectively implemented in a connectionless service. So we move over to connection-oriented service. Now in this connection-oriented service, the client and the server first needs to establish a logical connection between themselves. Now the data exchange can happen only after connection establishment. Now after data exchange, the connection needs to be terminated. Now the connection-oriented service at the transport layer is different from the same service at the network layer. In the network layer, connection-oriented service means coordination between the 2 end hosts and all the routers in between. At the transport layer, connection-oriented service involves only 2 hosts. The service is end-to-end. So this means that we should be able to make a connection-oriented protocol at the transport layer, either a connectionless or connection-oriented protocol at the network layer. So this figure shows you the connection establishment, data transfer, and then the termination phase in a connection-oriented service at the transport layer. We can implement flow control, error control, and congestion control in a connection-oriented protocol. Now here you see we have connectionless and connection-oriented services represented as FSM. FSM stands for Finite State Machine. This is Finite State Machine. Now the behavior of transport layer protocol, both when it provides a connectionless and when it provides a connection-oriented protocol, can be shown with the help of a finite state machine. So this figure shows representation of a transport layer using a finite state machine. Now using this tool, what happens? each transport layer, sender or receiver, is thought as a machine with a finite number of states. So the machine is always in one of the states until an event occurs. Now each event is associated with two reactions. Firstly, the list, which is possibly empty. So this list defines the actions which are to be performed, and it determines the next state. So it can be seen as the current state also. Now one of the states must be defined as the initial state, the state in which the machine starts when it turns on. So in this figure, we have used rounded corner rectangles to show the states. Please. And we have used the colored text to show the events. And we have the black text which shows the action. Now the horizontal line is used to separate the event from the action. This line. And later we will replace this horizontal line with a slash. The arrow shows the movement to the next state. Now we can think of a connectionless transport layer as a finite state machine with only one state, the established state. The machine on each end, that is both at the client and the server, is always in the established state, and it is ready to send and receive transport layer packets. Now, finite state machine in a connection-oriented transport layer needs to go through three states before reaching the established state. The machine also needs to go through three states before closing the connection. So the machine is in the closed state when there is no connection, and it remains in this state until a request for opening the connection arrives from the local process. Now the machine sends an open request packet. And this open request packet is sent to the remote transport layer and moves to the open wait I state. So you can say open wait 1, which is given in Roman. So open wait 1 state. Now when an acknowledgement is received from the other end, the local finite state machine moves to open wait second state. When the machine is in this state, a unidirectional connection has been established. But if a bidirectional connection is needed, the machine needs to wait in this state until the other end also requests a connection. So when the request is received, the machine sends an acknowledgement and moves to the established state. Now data and data acknowledgement can be exchanged between the two ends when they are both in the established state. So we need to remember that the established state, both in connectionless and connection-oriented transport layers, represent a set of data transfer states. So if we want to terminate a connection, the application layer sends a close request message to the local transport layer, and the transport layer sends a close request packet to the other end and moves to close wait 1 state. Now when an acknowledgement is received from the other end, the machine moves to closed wait 2 state and waits for the close request packet from the other end. Now when this packet arrives, the machine sends an acknowledgement and moves to the closed state. So there are several variations of connection-oriented finite state machine, and this topic we will discuss later on. And we will also see that how the finite state machine can be condensed or how it can be expanded, and the names of the states can be changed, how this is done. So this will be covered later on. And then we have transport layer protocols. So after this, we will discuss some of the protocols that are associated with transport layer. So I think this is sufficient for today. Up till now, if you have any question, you may ask. This topic I will cover in my face-to-face lecture, transport layer protocols. I will give you a brief introduction about them in face-to-face lecture, inshallah, next week. We still have time. If you want to ask anything, you may ask.